You know, I just asked. No, the ones her name is.
C. There we go. All right.
So how was the homework assignment? It was okay? All right. Okay, so what we'll do today is to go over the solution of the CNF homework assignment, and then I will assign the next homework assignment, which is actually proving the theorem. Okay, so we'll go ahead and do it in that particular order. And then when we have time left, we can continue with probability, because that's going to be our next topic. But probability is not in exam 1. So exam 1 only includes up to resolution and proof by contradiction. All right, so this is your homework assignment. You are given 3 well-formed formulae, and your job is to turn each one into a CNF, and then you combine those individual CNFs into one gigantic CNF. Now, some people just kind of do it in conjunction with of all of these, and then do the conversion in place after they're inside the one bigger conjunction. That works too. It's just a little harder to explain each step, because now you have 3 things going on at the same time. Okay, so what I'll do is I'm going to use the pseudo C notation. So this way it's easier to represent it, or it's easier to type it in using a text editor. There we go. All right, so the first one is P and Q implies R or S. There we go. So the first thing we need to do is to get rid of the implication. To get rid of the implication, you use the definition of implication, which you don't have to comment, because it's not one of the things that are in boldface in the note about the common forms. So if you do not explain this step, I cannot take any points off, because that particular rule was not in boldface. But but that's the reason why we can perform the next line. So we can say it is the negation of PQ or R or S. Is that okay? So this is so I do want to explain it here because I want you to understand how this works. So by definition of implication. All right, so now that we have a negation of a conjunction, it's really close to a CNF, but not quite, because we have a negation that is applied to a conjunction, and that's the reason why it's not a CNF yet. The rest of it is a CNF. R plus S or R or S is already in CNF. Okay, so we need to apply De Morgan's law. De Morgan's law, when you apply that, it is applying the negation to each individual component inside, in this case, the conjunction. So we have not P, not Q, but then the operator in between has to be changed from conjunction to disjunction. So now we end up with something like this. And the reason why we can do this is by De Morgan's law. Here we go. And at this point, if you want to say, okay, we are done, that's fine, okay? Because I did not say that you have to explain how you can remove the parentheses by the associativity of disjunction. But as one last step, I prefer to do it this way, but you don't have to do it in your homework assignment. So I would just go ahead and combine all of these into one single one without the extra parentheses, because of associativity. And as a result, there's no need to specify the ordering of operation, because any order you want to do this is fine. Is that okay with the first sub-expression? So with the second sub-expression, it's even harder. For those people who always kind of think that I always ask tricky questions, because it's not. It is already a CNF. because it is a disjunction that only consists of variables and the negation of a variable. So as a result, it is already a CNF. It's done, okay? So that leaves us to the last one. So the last one is the negation on the very outside, and then we have R and P or S in the inside, okay? So with this one, you have, well, I suppose you do have a choice of applying distribution in the inside first, or you can apply the De Morgan's law on the outside. I would do the De Morgan's law from the outside. So then it becomes not R or the not of P or S. Okay, is that okay? Because you have R as one component of the conjunction, P or S together is another component of the conjunction. De Morgan's law is basically distributing a negation into the inside of the operation, but you have to change the operation too. So this is also De Morgan's law. Yep.
But it's okay to use the other one?
It's okay to use the other one. You can distribute RPS first, so it becomes RP plus RS, and then you do the negation on that. That works too. It works exactly the same way. So this one has not R on the outside, and now we have to apply De Morgan's law again into this one. So we have not P, not S, because you are distributing the negation into the interior of the disjunction. But because of De Morgan's law, you also have to change the OR into an and we look at an and like it's a multiplication. So this is what it looks like. So once again, this is done by the Morgan's law. Okay, so at this point, we can use distribution. So distribution is interesting in Boolean algebra because it works in both directions. In arithmetics, it doesn't work like this, but in Boolean algebra, it does. So in this case, we can distribute it so that we end up with not R, not P, or not R, not S. Distributive law. And at this point, we do have, it's not CNF yet because we have a conjunction. Let me see, does that look right to me? Nope, it's a, let's see, nope. There we go, okay. I distributed it in the wrong order. Best of the operators. So I think it is correct now. Is that okay? Say again? Oh, okay.
Isn't it, if you use De Morgan's law again, wouldn't you put, can't you use De Morgan's law again? Instead of having nots, P or S, you could put not nots, and then have not R.
Putting a not here?
So, right there, instead of leaving it like that, you see using it again, so you get R, and.
But there's no negation to apply to use De Morgan's law. De Morgan's law requires a negation on the outside. The negation has to apply to a disjunction or a conjunction.
Okay.
So unless you introduce negations like that, then you can use De Morgan's law, but it won't get you anywhere.
Okay.
Okay. Is that okay? Is that what you guys got to? I think so. I think that's what everybody got. Okay. So now we have 3 CNFs. We have this one representing this well-formed formula in the original question. We have this one which is already in CNF representing the second well-formed formula. And then we have this one representing the third one, and this is probably the trickier one, representing the third one. And all you have to do, as one single CNF as the answer, is to put all of these together. Okay, so you basically just say something, and then we just copy the rest. So the first part is this thing here. You do have to put it in parentheses because copy too much. There we go. And then the second one is just this part here. And then the third part would be these two together. So that's the final answer. Are there any questions about the final answer? And then somebody brought to my attention that Wolfram, doesn't give you the same answer. And that's because Wolfram actually does a step of simplification, which is actually is doable also using resolution. But I only want you guys to expand each one into a CNF and then just combine all the CNFs together. So this is the answer that I'm expecting. Is that okay?
Can you repeat that?
Sorry?
Repeat what Wolfram did?
Wolfram, somehow, gave a answer that is different. So Wolfram, actually simplified between this one and I think one of the other ones. But basically, it simplified into a different. It combined two of these into one, which is one step that you can also do using resolution. But this is the answer that I'm expecting. All right. So are there any questions at this point? So with the first homework assignment, there is no need to apply resolution. There's no need to negate the theorem because I did not give you any theorems to prove in the first homework assignment. Yep.
So does that mean you only use resolution when you actually prove you don't use it when you're writing the CNF?
That's correct. So resolution is one of the links in a proof. Remember, I think I drew it at about the same place here. In a proof, okay. So in a proof, you have everything in iota to begin with, but because all of these things are true at the same time, there's always an implicit conjunction connecting all of these things. And then here's your theorem that you're trying to prove, but you have to negate the theorem. And the objective is you want to show that all of these things will lead to a contradiction. So how do you get to a contradiction? You use resolution. But what is resolution? Resolution is just one way to do a implication. Do you see what resolution really is? It's an implication. This combined with that implies this. But using resolution, this form here just by syntactic manipulation. So when you chain all of these resolution steps, each one is a resolution. So when you chain all of these things, and eventually you get to a contradiction, you get to false, that means everything are connected by implications going from left to right. Which basically means you can now say these things, including the negation of the theorem, implies contradiction. And that's how proof by contradiction works. So that's why when you're not proving anything, there's no need to apply resolution. So in this particular homework assignment, I just want you guys to turn everything into a CNF so that we are ready for the next homework assignment where we try to prove a theorem or prove that it is not a theorem. Okay, all right. So are there any questions about this particular homework? Yep.
For a disjunction of variables, does one of them have to be negated, or can they both just be non-negated?
No, they can be negated or non-negated.
Okay.
Yep. So you can have a whole group. We just don't have one that has everything non-negated. But if it turns out that your expressions has one of those things, that's fine too. Okay. Any other questions? Yep.
Is it okay if we started with them, like grouping them together and then using the laws and then ending up with the CNF?
You mean just combine all of them first and then resolve those? Yes, that's fine. But it's harder to explain because now you have a longer CNF to begin with. So how you go from one step to the next step, it's harder to explain where you did the transformation.
Okay, so it's better to keep them split up.
I personally like to do it like this, so I have a smaller problem to solve, and then I combine all these sub-solutions. But if you start off with one conjunction with all of the given well-formed formulae, but you still explain how you got from one line to the next, it will still be okay. Yep. Yep. Mm-hmm.
So on the exam, you want us to write like this, or you want us to do it one?
As long as you can show how to convert a non-CNF well-formed formula into a CNF well-formed formula and show that you understand how that process works, it will still be okay.
If we perform multiple laws in one line, would that be okay with you?
You will still have to explain to me. I have to be able to see that you apply, you know when to apply which rule. Yep.
Is stating De Morgan's law twice, do you have to state it twice?
Yes, you do, because the first one in this case is this negation combined with this conjunction. That's this application of De Morgan's law. The second one is using this negation on this disjunction, and that's why we have another De Morgan's law. So I never really combined two De Morgan's law into one single one. Just so that it is step by step. Doing things step by step makes it easier to debug the process, because otherwise if I jump one step and I make a mistake, it's harder to spot, where I make that mistake. All right. And yep.
Could you, because I did it start with like one single conjunction, so, but where you have on the last, in the last well-formed formula and the first well-formed formula that you did, you have a step that does Morgan's law. I guess, like, if you put it as like one axiom, can you use that? Can you modify two parts of the equation with the same axiom off of the same law?
Oh, I see. So you're basically using one single transformation, but you're applying in parallel to multiple parts in the same expression. I guess it would be okay. Because that I can still see what you did to those expressions. Yeah, but personally, I just prefer it this way because there's no doubt what happened between the lines. All right. Any other questions? We are all good on this one? Okay. Well, if you do have any questions later on, just let me know, and we can always come back to revisit this one. And according to the statistics, 39 out of 46 people turned in this homework assignment. There are only actually 45 of you, because I actually am one of the students in the class too, my other account. So there are only 45 students, and 6 people basically did not turn in anything. All right, so let's move on to the next one. This is your current homework assignment. You have 1 week to work on this. I don't think it will take you 1 week to work on this, okay? I think it will take you less time, but I will just give you 1 week. So the theorem that I want you to prove is this one, and this is a continuation of the homework assignment that we just did. In other words, you can either use your own solution of the homework assignment that was due today, or you can just copy this and use this as a starting point. Okay, it's up to you. Okay, if you think your answer to the first homework assignment is right and you just want to use it, no problem. If you want to be sure to start with a known solution, you can use this one as well. It's up to you guys to decide. So when you read the homework assignment here, so this assignment requires that you use resolution and proof by contradiction to get the job done, because I need to prove whether this is a theorem or not, okay? In other words, there's no guarantee. I'm not telling you whether the negation of P and R is really a theorem. It is implied by all the 3 well-formed formulae in the previous homework assignment or not. So there's a chance that it is, and there's a chance it is not. It really should not bother you one way or another, because the whole thing about resolution is it has to terminate. At some point, either you're stuck, which means no matter how you apply resolution, you cannot come up with any new components in the CNF, or you resolve to a 0, and therefore you end it as well. So regardless, your whole process should end at some point. So what you need to do, this is a reminder, start with the negated theorem or the negated proposed theorem, because it may or may not be an actual theorem, as a CNF, and then you combine the negated theorem with the rest of the CNF, which is my answer over here. And in each step of the resolution, I want you to clearly indicate which 2 clauses you're using to perform the resolution, and which variable is used to join the clauses. Okay, because in some cases there may be multiple variables in both clauses that can be used for resolution. So you need to point out which one you are using for resolution. Which also reminds me whether the following. What are you going to do with this resolution? So I'm going to show you this. So let's say this is a whole completely different example. Okay, so it's not related to the homework assignment. I'm just using this to illustrate the concept. So let's say one is P or Q, the other one is not P or not Q. Okay, what do you do about this? Okay, obviously you have a few choices of resolution. The question is, can I resolve this to contradiction right away? Can I resolve this to false right away? What do you think? The answer is you can only use one single variable for resolution. So you can either pick P and not P and use it to resolve, which ends up with Q or not Q, or you can use Q for the resolution, which means you get rid of the Q and the not Q, then you combine the P or the not P. Okay? But either way you end up with true. Either way you end up with a true statement. In other words, if you look at this, okay, there are two ways to proceed. One way to proceed is to use the P, the variable P, as the glue. Okay? So in that case, you end up with the same thing as before, but then you also end up with one new term, which is the result of the resolution, and that one is going to be Q or not Q, which is not useful, right? But the other way to do the resolution is to repeat the first part, okay? Because resolution does not take away anything. It just adds additional terms to the whole CNF. And in the second one, you have P or not P. So you can go in either direction, but you cannot just say, oh, they annihilate each other and then we have a false. It doesn't work that way. Is that okay? Does everybody understand what I mean by you can only choose one single variable for each step of resolution? Because if you can choose two, then you can say, oh, P, Q, are annihilated by not P, not Q over here, so we end up with a false, and hence we have a contradiction and of proof. It doesn't work that way. Is that okay? Now, if I take this one step further, then I can say this step doesn't really do us any good because this is always true, which means we are really just getting back to the original expression. We didn't get any further in this case. This application of resolution did not result in anything new. Is that okay? Because P or not P or Q or not Q, both of those simplifies to a true, and a conjunction with a true does not change the meaning of the conjunction at all.
So we can just take it off?
Right. So this resolution did not gain us anything because Q or not Q is just true, but with a conjunction with true does not do a single thing. It doesn't do anything useful. So that means this basically simplifies back to the original form. We did not do a single useful operation at all.
So if this happened in our homework, then we would say that the proof is failed.
Then you cannot get to the false, and as a result, the theorem is not a theorem. The proposed theorem is not one. If this is what you ended up with, with the homework assignment, then there's no way to proceed anymore because you try to resolve using P, doesn't get you anything. You try to resolve using Q, doesn't get you anything either. And that you have already exhausted all the possible ways of resolution. And since you cannot make any further progress at this point, and yet you do not have a false at the end, so that means you cannot get here, and you know for sure that there's no way to get there also. So now you can conclude and say that the theorem, whatever the theorem originally was, the proposed theorem is not a theorem. It's not implied by the stuff in iota. All right. Any questions about? Yeah, go ahead.
So for the homework, you have prove not P and R.
Yep.
In the first step, you said negate the theorem.
Mm-hmm.
So would we negate the theorem, like not P and R as the first step?
Mm-hmm.
Okay.
Yep.
So, if we go back to that example,
Uh-huh.
what theorem, the example that you were doing, what theorem were you trying to prove?
I did not identify which one is the proposed theorem. It could be this one, could be this one, but at this point it doesn't really matter. Because at this point you cannot differentiate which part is the negation of the proposed theorem and which part is the iota itself. We just look at this whole thing as one single CNF, and we cannot distinguish which one is which. Yep.
So when we come up with a new theorem, how do we choose the axiom so that we're able to get to the conclusion that the theorem is valid?
Say that one more time.
So, for example, you just came up with a random theorem like that. How do we?
But there's no theorem. I'm just illustrating the mechanism of resolution. This has nothing to do with which one is a theorem and what I'm trying to prove. There's nothing I'm trying to prove here. I'm just illustrating resolution can only work on one single variable at each time. You cannot apply resolution on two variables at the same time. That's what this is illustrating. Yep.
Will you be giving us the axioms to work with when you, if you provide us with a theorem and tell us to work from there?
But there are no axioms anymore because you're just getting the axioms from the current homework assignment. But there are no axioms like De Morgan's law or distributive law or associative law. Those do not apply anymore because we only have one single way to proceed, which is resolution. Okay. Any other questions about the homework assignment?
For that one, would it be wrong to use De Morgan's law to try to solve?
The Morgan's law cannot be applied either because the negation is not applied to a disjunction or conjunction. The only negation is applied to a single variable and a single variable, so there's no way you can actually use the Morgan's law in this case.
It can be used in reverse.
In reverse?
You can't add a negative to the whole.
Okay, I see what you mean. So when you apply the Morgan's law, you can basically look at this thing and say, okay, let's look at this as, oops. So you can say, that is P or Q, and then the negation of PQ like that.
Yeah.
Okay.
I mean, it doesn't really get us anywhere.
You can, but then you're not using resolution to prove a theorem. I mean, because these are all equivalent expressions, which basically means this expression here, this well-formed formula, has exactly the same meaning as this well-formed formula, but neither is going anywhere. Because what we really need is to be able to get to a false in order to use proof by contradiction. So in your homework assignment, you don't need to do anything like that, because all you really need to do is to use resolution to go to the next step. Yep.
Will we always be given the CNF to
Well, I'm breaking up one single question into two parts, right?
Yeah.
So the first part is due today, which gives you the CNF.
Right.
And then the second step is to apply resolution to see if you can get to a false, to use proof by contradiction.
So like on the exam, could we expect something like this?
Yes.
Okay. So like two different broken up things.
Yeah.
Okay.
In the exam, I'm contemplating whether to give you guys a question like, okay, this is the CNF, okay? So come up with a theorem that is implied by this CNF. So it's kind of like a reverse question. It's kind of like, I'm being too lazy to actually think of a question. So I will have you guys to think of a question. It's like, okay, come up with one expression that is an actual theorem and come up with another one that is not a theorem.
So, you want us to figure out, you want us to figure out the theorem from the CNF?
Well, okay, I'll give you an example.
Cool, but
That is cool, but I like the but part. Okay, so in other words, okay, look at the homework assignment, the solution of today's homework assignment, right? So this is what we ended up with. So now, if you think if you're in my shoes, right? So I have to give you a homework assignment. I have to give you something that is either a theorem or not a theorem. So then you have to go through the process and either prove that yes, it is a theorem because we can actually resolve all the way down to false, or we can resolve all we want and it doesn't go anywhere, right? So the question now is, if I give you this as the iota, right? This is a representation of iota. Can you give me an expression that is actually a theorem? And how would you go about doing it? So I'm not, I'm just, contemplating. I'm not, actually going to put it into your exam. I have not decided yet, but that's one of the possible questions. Yes?
Can you show like how, because you mentioned that you want us to explain what clauses we're using in our resolutions. Can you just like give an example of how you want us to type that?
The way I do it in my notes is kind of the preferred way. You can use the underbar if you want to, but it gets a little harder to type if you just want to use plain text. So let me go back to my notes first, so I can show you what I did in my notes, which is this one. Okay, so when I did it, I used, oh, maybe not, the one next to this. Okay, the one next to this is, okay, this is resolution. There we go. Okay, so this one, so with this one, what I did was I used an underline to indicate which variable is the connecting variable, and this is the result. So something like that would work.
Okay.
Because if there's an underline under a particular variable, it is telling me that this is one of the glue pieces. So that means this clause is one of the clauses that we are joining. And this is also, the other part of the same variable. This is negated, which basically means this is the clause that I'm using to make the connection. So in other words, I'm concatenating this expression and this expression into this one here, because I have to toss away Q in this case, because one side has Q, the other one has not Q. Yep.
So that wasn't just something you did in your notes to clarify it. That's an actual writing convention that they used.
Correct.
Okay.
But you can use other means to do it too. You can label, all your clauses, and then you say, okay, combining the first one and the third one using this variable gives us this. So there are different ways to represent the steps of resolution, but in either case, I just need to know which variable and which clauses are you using for that particular step of resolution. How you want to express it is up to you. It just has to be clear enough for me to see that, okay, I can see that you know how to do resolution. Okay, good questions. Any other questions about the homework assignment? You have 1 week to work on this. And I can see some of you guys are either taking notes, playing video games, or working on the homework assignment, or all of those at the same time, all of the above. It's not supposed to be a very hard homework assignment, because at this point it's really fairly just mechanical. Okay, all right, cool. So with that topic gone, we are going to continue the discussion of probability and see if we should play lotto. One state, not California, I think one state has a jackpot of $448 million. Which state was that?
We just sold it.
Today, yeah.
I don't know which state. I really do.
Yeah, so I think it's a Powerball lotto, right? Yep. Let's look it up. So Powerball lotto, and I think it's 448 million. I could be wrong. Oh, I got the right number.
That's 2013. That's 2013.
That's 2013. Wow, that number matches though. 2013, but that was.
You could try seeing if there's juniors on it.
435. Indiana, that's it. 15 hours ago. So I was pretty close. 400 something million dollars, right? I have no idea. So this is Powerball, and we'll talk about Powerball today. You know, how do you know the probability of winning in Powerball? They give you the chances already, but how do they come up with that number? That is what we're going to work with, okay? So the Powerball number is 10, 13, 28, 52, and 61. And the special number is 2. So the odds of winning is 1 in 292.2 million. And this is great. According to the Associated Press, it's not some professor teaching statistics or discrete structure. It is the Associated Press. So do you trust the press, the news, for something like this, or would you rather trust a scientist or mathematician? Okay. So, but they haven't really disclosed one really crucial factor. Because once they figure out, how many winning tickets there are, then we can actually figure out, whether it's worth it to play or not. Because with only one single winning ticket, it seems like it's kind of borderline playable, because a lot of these $435 million will be taxes. Right? Uncle Sam wants his share, and the more income you have, the more percentage of your income is going into taxes. So out of $400-something million, you really do not even get close to 75% of it, maybe 60%. I don't know. Does anyone know your taxes? Does anyone make close to like a few $100 million a year?
So California tax on gift.
Huh?
Lottery's treated like a gift. It's gift tax of like 47%.
40,
7.
and that's just federal or combined?
It's combined state and federal taxes. for
Okay,
California.
47%, so you only get to keep 53% of this amount, which is not worth it anymore. Because if you look at the chances, right?
Because you also have the option of like taking a payment, taking a payment yearly over the course of how many years, and tax laws may change in next subsequent years. So you might get a bigger percentage every year if the gift tax gets less.
But then you run into the risk of not knowing how long you're going to live.
But they continue. You get a step-up basis.
And you cannot take this with you.
You give it to your heirs, and they get a step-up basis. So
Okay.
like capital, they won't get charged. It's like the step-up basis means that more or less it's like all of it's their principal. So
I see.
They would be tax exempt once you die.
I see. All right. Well, let's go ahead and check this out. We'll check out Powerball in Indiana and figure out the chances of winning. Okay, so that's what we're gonna do today. So we go to Indiana Powerball Lotto, and hopefully we'll get to the actual website itself. Okay. So let's see. Yep, there we go. All right. And we want to look at the rules of the game. Okay, they have to disclose that somewhere. Powerball numbers, how to win the lottery. Okay, there we go. Yeah, that's an ad. But that's all. Ad choices. There we go. Okay. Because I want to figure out the rules of the game. They have to disclose the rule of the game somewhere.
Predictions.
Lottery predictions. I need to install ad block.
Well, this thing's legit.
Oh, where to play? I need to know how to play, not where to play. Powerball. Okay. Where are the rules? I know in California they have to tell you how to figure out this number, because I need to know what is the range of numbers for each ball. That is important. And there we go. Okay, so the ball pool has 69 balls, adding another 10 numbers. However, at the same time, the Powerball pool decreased. What?
Maybe at the very bottom they have like an FAQ.
Oh, the actual Powerball goes from 35 to 26. Okay, so the first 5 numbers can be, there are 69 balls to draw from in order to get the first 5 numbers, and then the actual last number, which is called a Powerball number, is going to go from 1 to 26. There we go. Okay, so that's my understanding. Let's see whether that works or not. Okay. All right. So let me just kind of restate the game or as I understand the rule of this game. Okay. So let's scroll this stuff out of the screen. Okay. So the Powerball Lotto is based on 5 numbers, if I remember correctly. Okay, let me just 1, 2, 3, 4, 5. Yep. So there are 5 numbers. So Powerball game is basically draw 5 numbers from 1 to 69, and then draw one single, what they call Powerball number from 1 to 26. There we go. Okay, and the important part here is without replacement. Okay, and I'll put this in double quotes because that is actually important. Okay. Okay, so these are the rules of this game. So you basically put 69 balls labeled from 1 to 69 into a cage, and then you use a mechanical thing to draw 1 ball out each time. But once you draw a ball out, you do not put it back into the cage. So you have to draw 5 out of the cage. Is that okay? The order does not matter. Okay, so if you whether you draw a 1 first or 15 first doesn't matter. As long as you have 1 and 15, it is considered the same combination. And then after that, you put everything back in the cage. But you only put 1 to 26 back into the cage, and then you draw 1 single ball out of those 26, and that becomes your Powerball number. If you match all of the first 5 numbers and the Powerball number, then you win the jackpot. Is that okay? I believe that's the rule. Okay. So the question now is, how many possibilities do I have for the first ball that I draw out of the cage? Okay, remember I have 69 balls, right? Initially, I have 69 balls going from 1 to 69 in the cage. So when I draw the first ball out of the cage, how many different ways can I choose from? 69, right? Because that's basically the whole thing. So we have 69. And what about the second one?
Oh, you have 68 now.
68. And then the third one is 67. And then 66. And then 65. Does everybody understand why I have 69 choices to begin with, but once I have 1 ball drawn, there are only 68 balls left. So that's why, for the second ball, I only got 68 choices. But once I have 2 balls out, then I only have 67 balls left. And then 66 and then 65. They are multiplied because they're independent, okay? One of the balls from the first draw does not influence what I'm gonna draw from the second one. So, regardless of what I'm drawing from, which ball I took out from the first draw, I still end up with 68 cases in the second one, and that's why I have to multiply to get me all the possibilities. Is that okay? And I'm going to put this all the way out. The Powerball itself has 26 possibilities. Now, there's a reason why I have to put this all the way out, because I want to express something. Because the way it is expressed right now, 68 times 69 times 68 times 67 times 66 times 65 is distinguishing 1, 2, 3, 4, 5 considered to be different from 5, 4, 3, 2, 1. The way it is calculated right here, it is computing 1, 2, 3, 4, 5 as one of the possibilities, but it's also considering 5, 4, 3, 2, 1 as a different possibility. How do we know that? Well, because the first one is 69. How does it have 69? Because I can have the ball of 1 as the first ball, I can have the ball of 2 as the first ball, I can have the ball of 3 as the first ball, I can have the ball of 4 as the first one, I can have the ball of 5 as the first one. But that means I can start with a 5, work my way down 5, 4, 3, 2, 1. It is considered one of the possibilities of this number. But I can also draw it like completely random. 1, 2, 3, 5, 4. Okay? It's considered another possibility. But that's not how the lotto game works. Because when you buy a ticket, those numbers are always sorted. Right? So now the question is, if I just pick 5 different numbers, how many ways do I have to arrange those 5 numbers? Okay? So this is a sub-question. Sub-question. If I get 5 numbers,
5 factorial.
okay, how many ways can I arrange those numbers? Okay. Now these 5 numbers are all distinct. Okay, so let me just add it here. 5 distinct numbers. Okay, there we go. So out of the 5 distinct numbers, I have 5 times 4 times 3 times 2 times 1 way of arranging those. In other words, if I start with, okay, let's not deal with numbers. If I start with A, B, C, D, E, okay, and I want to see how many ways can I rearrange the letters where the ordering is important, then the possibilities are 5 times 4 times 3 times 2 times 1. Right? It's 5 factorial, otherwise known as 5 factorial. So that means this number needs to be divided. Okay? So I'm going to approximate division here. It has to be divided by 5 factorial because for each possible number, for each possible combination where the ordering really should not matter, there are 5 ways to arrange it. And the top number is including those 5 factorial different ways of arranging the same 5 numbers. So I have to take that into consideration and divide it by 5 factorial first. Is that making any difference? Making any sense? Sort of? Okay? All right. So let's check out this number and see whether it comes out to like 290 something billion. And the best way, the quickest way that I know how to do this is a spreadsheet. See, spreadsheets are really useful. It's just a big calculator. And if I do it in Google Documents, you guys can see it as well. So I'm going to go to my 440 class with a shared folder, and I'll just go ahead and create a new sheet here. And we'll call this Lotto. Okay. Name it as Lotto. There we go. So you should be able to find it now, because it's on the shared drive at this point. The best part out of this is, even your cell phones can now access those Google Sheets. So even with a cell phone, you can actually follow along with all this stuff. Okay, so we'll go ahead and look at this. Okay, so we have 69. Okay, there's an easy way to do this, but I'm not going to do it the easy way. So I will have 69 times 68 times 67, 66, 65, and then divide this whole thing by the factorial of 5. And then multiply this whole thing by 26 because the Powerball by itself has 26 possibilities. And the number turns out to be, aha! Okay, we got it. 292,201,338. So we'll double check with that because I think we can go back to the news here. Yep. In fact, our number is better because they have they cut off the precision at 292.2 million when the number really is 292.201338 million. Yes, so we did better compared to Associated Press. Yes. Is that okay? Does everybody understand how those numbers are calculated? With at least Super Lotto. Yep.
Why did you divide by 26?
Divide by 26? Multiply. It's a multiply.
Okay.
Yep, because the multiplication is not a part of the division. So this is the division, and then I multiply the quotient by 26. It looks like I'm dividing by 26, but that's not the case. Because division and multiplication have exactly the same priority level, so they're performed completely sequentially. They're not grouped. All right. Are there any questions about this particular calculation? Sort of. Yes?
Yes.
Okay, so, I mean, is this important? Is this worth your money and time to take this class already? Knowing when to buy lotto? Okay, the problem with lotto is they can issue multiple tickets of exactly the same numbers, which means when you have when you have a lot of money in the jackpot, you can have multiple winners, multiple jackpot winners. So the $400-something million will be split n-way, depending on n is the number of people with a winning ticket. So that means your actual chances is not 1 out of close to 300 million anymore. Well, your chances is still the same, but you're not winning the jackpot. You're not winning the entire jackpot. Yep.
There are also duplicate losing tickets, right?
Say again?
Are there duplicates of losing tickets?
They're duplicate of tickets, yes. So even though there are only 300 million possible tickets, they can issue like 600 million tickets. Because the tickets are printed at a 7-Eleven, at the point of sale, right? At the POS. So that means, whenever people walk in, the machine will just print out another ticket. So it is possible for, to sell more tickets than there are possible ways to arrange the numbers. So then you end up with duplicate numbers or duplicate numbers on the tickets, and people with the same winning tickets can go cash out the jackpot. So the jackpot has to be split in those cases. So historically, when you look at high jackpot lottos, they always almost always end up with multiple winners. Yep.
Is it possible to buy enough tickets to guarantee a win and still profit from it?
That's a very good question. Okay, so the question is, if I just go to a 7-Eleven and I say, hey, dude, just here's 300, close to $300 million. Print me every single possible ticket. Okay? Of course, a whole line is going to form and there'll be a little riot outside, but I don't care, right? So they can write all they want outside. I want my 292.2 blah 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 million tickets. So yes, you can do that. But guess what? If the jackpot is high enough for you to think this is worth doing, somebody else may be doing the same thing in another 7-Eleven, right? So, but because there's no way to model how many people will buy a lotto ticket based on the jackpot. Now, if there is a function to do that, to map the jackpot money to the probability of how many people will buy tickets or how many tickets will be sold, then you can factor that in and say, okay, should I play or not? But since that function does not exist, or nobody has the numbers, so that means there's a big variable that you cannot account for is how many tickets are going to be sold. Because when the jackpot is high, most people would pool. Okay, so this class may pull together and say, okay, let's each person will pony up like $50, and then we'll combine the whole class to have like 50 times 40, which is what, $2,000 or something like that, right? So we'll combine $2,000 and buy 2,000 tickets. So as the jackpot goes up, the probability of people actually buying a ticket also goes up. But that function is not known. Is it linear? Well, most likely it is not going to be linear. Okay, but since you don't know that particular function and you have no idea how many tickets will be sold, I can almost tell you for sure, with a jackpot of $400-something million, more than 300 million tickets are sold. Because almost every single time they end up with multiple winning tickets, jackpot winning tickets. So that's the part that cannot be done in this class, because we can understand the probability. but we cannot map out the likelihood of people buying tickets. So that was a very good question. And anyone with that statistics will be very will be in a good position. Yep.
Even if you were the only one to win, you'd still lose.
Because of taxes.
Yep.
Right. Yep. If you buy every single ticket. So that's why, we have people thinking, well, I don't know about the rest of the people. I am more lucky than the rest. So my chances of winning is actually higher than the rest of the people. Well, that's why people go to the casino. Okay, if you go in, just for entertainment purposes, that's one thing. But some people actually think that they can end up with more money, going, to gamble or buying lotto tickets. Sorry?
They're playing poker.
There are certain games where you can actually analyze the probability and actually have a slight chance on your side. But if you think about a casino, all the shiny lights and all the drinks and whatnot, somebody is paying for that stuff, right? And it's not the government. So you kind of understand that, okay, in most cases, you're going to lose.
But you have more control.
Hmm?
There's still some. I
Hope
just
you're
feel
not
like
betting against the house, we're betting against
it's
the
not
business.
as futile as the lottery.
If you can count cards, yes. Okay. In other words, if you can improve the chances of you winning, so that it is, so that it's favoring on your side, yes. But if you have those techniques or have technologies to do that, the casinos will notice that and kick you out of the casino. Have you guys watched that movie, Rain Man? No? It's an old movie. You guys are too young. That's why. Okay, so this is a good movie to watch. I'm an old man, yes. But this is a movie that you can watch, regarding that particular part. It has got Dustin Hoffman and Tom Cruise, basically as, I think they're brothers?
They're brothers.
Yeah, they're brothers. Okay, so Dustin Hoffman has a condition. Somebody spilled toothpicks.
He sold toothpicks.
Yeah, so
And he
somebody
got them.
spilled toothpicks and he can count, the number of toothpicks almost instantaneously. So they took him, Tom Cruise, took him to a casino because he can count cards like nobody else can. So they ended up actually making money because, he was able to decide when to call for a card or not a lot better than the next person. Because he can count what cards have been played already. So the chances of the next card being, a certain number or less than a certain number, he can calculate that. So they were making a lot of money from the casino, and then they got kicked out. So card counting is definitely something that casinos will frown upon, and if they find people are doing that, they will kick people out. Now you can say, well, but I'm not Rain Man. How am I going to count cards? You don't have to do anything like that, right? I mean, you just need a camera on your lens, right? I mean, have that feed, to somebody on the outside, and somebody's going to punch it into a computer. What do you mean by counting cards? We don't count cards. We just have pattern recognition and powerful computers, and just have a live feed, to that computer. So, if you do that, the casinos will kick you out. Now, whether they will beat you up or not, that's a whole different question. But they definitely will kick you out. Does that make any sense? Okay. All right. So what this is showing us is a very important concept. Two important concepts. Is the concept of factorial, combination, and permutation. So what we'll do next is to introduce those particular terms and the equations of each one. And we are not running out of time. Good. Yeah, to cheat in the casino these days, people go high tech. I mean, they don't need to rely on the memory of a person. They can actually just go ahead and cheat their way in the casino. And we are in discrete probability. All right. So this slide talks about combination and permutation. So the equation is like this. Okay, so let me see if I can just zoom into the equation of permutation. There we have it. Okay, so this is the equation of permutation. It is based on factorial. So P and R, like that, okay, and sometimes people put the N and the R in parentheses, is basically you're given N items, N distinct items, you're choosing R out of those, and the question is, how many distinct permutations can you get out of this whole thing? Now, when we talk about permutation, ordering is important. In other words, permutations are kind of like tuples, okay, where the ordering is important. When we talk about combination, then the ordering is not important, like in a set. Okay. So in this case, we start off with n factorial, and then we divide it by n minus r factorial. It doesn't seem to look like it makes a lot of sense, but it does. Okay, because we just did it. So we have 69 times 68 times 67 times 66 times 65, right? This is the number of permutations when you have 69 balls in a cage, and you want to look at how many ways can we draw the balls out of the cage, 5 balls, and the ordering is important, okay? But when you look at this number, you can basically say, oh, the number is the same if I just multiply by 1. Okay, that's kind of trivial. But what is this 1 here? What about this 1 being 64 factorial? Okay, 64 factorial divided by 64 factorial is a 1, and anything times 1 is that original thing. Does it make sense? But now I can say, oh, what if I combine this portion with 64 factorial? What does it become? It becomes 69 factorial, right? Divided by 64 factorial. Okay? But where's the 5? The 5 is the number of things that we are drawing out of that cage. So that's why, in this case, n is 69, r is 5, and this number is the permutation of choosing 64 things, 5 things, choosing 5 out of 69 things. Are there any questions about the permutation notation? It's good, okay. So what about combinations? Combinations are discussed down here. So combinations turns out to have 3 ways of representing it. So the first one is just a C and then with the N as a superscript, R as the subscript. The second way is this way, which is kind of weird. This is known as N choose R. Okay, so when we say N choose R, it is implicitly talking about combination where the ordering is not important. Okay, so we're choosing R distinct items out of N, but the ordering is not important. And you can see permutation in this. Because when you look at this part here, n divided by n minus 1 factorial, that's exactly the permutation. So we're really just taking the permutation of choosing r out of n things and then divide it by r factorial. But why are we dividing it by r factorial? Because for each distinct set of r things, there are r factorial ways of reordering the things. So we just have to say, oh, okay, so we have the permutation like this, but in order to figure out the combination, we'll just have to cancel out the duplications. So for each combination of 5 balls, there are 5 factorial permutations. So when you look at the number of combinations, you just have to divide the number of permutations by the number of permutations once you have chosen those 5 objects. But the definition of combination is n factorial divided by r factorial, and then in the denominator you also multiply that by n minus r factorial. Yep.
You already gave us the example of combination. Can you give us the example of permutation?
Permutation is important when ordering is important. So you have to think about the real life cases where ordering is important, right? A, B, C, D, E is different from, spelled backwards. D, C, B, A. The easy one is route planning. Okay, let's think about route planning. All right. So let's say you're running a pizza shop, okay? So you run a pizza shop, and the pizza shop is right in the center of a densely populated area, okay? So at any time you have some pizza delivery that you have to make. So let's say we have 4 delivery points, A, B, C, D, okay? So because A, B, C, D are not linear like this, well, there's no clear advantage of going to one particular one first, okay? So we got A, B, C, D here. So now the question is, how many different ways can you plan your trip? Okay, because you're starting from here and you want to end up to the pizza shop. So how many different ways can you consider in order to choose the optimal way to deliver pizzas to the points A, B, C, D? Well, how many destinations are available as choices as the first destination? There are 4, right? How many can you choose as the second one? 3, 2, 1. So you have 24 possible routes to consider. That's permutation, because ordering is important. Does that answer the question? Sort of?
I was thinking about the formula that you just gave us and a simple.
Well, in this case, it is the permutation. It is the permutation of using 4 out of 4 things. Because when you have 4 out of 4, by definition, what is permutation? It is 4 factorial divided by 4 minus 4 factorial in this case, so you end up with just 4 factorial. But it is still permutation. But this one is kind of interesting because this is also called a traveling salesman problem because it doesn't scale very well. If you have 5 destinations, how many different ways do you need to consider? It's 5 factorial, okay? So when people think about 4 versus 5 factorial, it's no big deal, right? Okay, well, but in reality, 5 factorial is 120 as opposed to 4 factorial, which is only 24. What about, if I add, I just got a bigger delivery truck, I can now make 6 stops. How many ways can I make deliveries? 720, okay? So with 4, because there are only 24 possible ways, somebody can actually do it by hand, right? Somebody can just look up Google Maps and do all the calculations, distance-wise, time-wise, and look up and find out which one is faster. With 120, which is 5 destinations, you probably don't want to do it by hand. With 720, it gets worse, right? What about UPS trucks? How many stops do you think a single UPS truck needs to stop on an average day? So we're not talking about Christmas.
At least over 100.
Okay, it's at least 100. So we are talking about, if we apply the same algorithm, it's going to be 100 factorial. And we do not think about 100 factorial as too different from 5 factorial. It's like, oh, at the worst, it's only 20 times worse, right? No, 100 factorial is a huge number. How big is it? My old calculator, when I went through high school, okay, my calculator can only compute up to 69 factorial because the exponent in base 10 is 98 already. The next one, 70 factorial, is going to overflow the calculator because the calculator cannot handle a exponent of 10 that is more than 99, which is already a big number, but your calculators can probably handle that. Okay, so we can, since we have the spreadsheet up and running, let's go ahead and check out the spreadsheet and see how big of a number we're dealing with. So we just say the factorial of 100. Well, that's a pretty big number because it is 9.3 something times 10 to the power of 157. Okay, So the question is, so now the question is this a problem with the algorithm? No. This problem itself is the problem. There are no known fast way or practical way to deal with this. Okay? This is also when you start to get into NP-complete problems. How many people have heard of that term before? Okay, 1 or 2, 3. Okay, so NP-complete is describing a whole class of problems. It's not describing a single problem, but it's a whole class of problems where each problem can be transformed into another problem of the same class using what we call polynomial time. But ironically, NP-complete, the P of NP, is really just polynomial. Yeah, NP, okay, the P actually stands for polynomial. Polynomial. Polynomial basically means the execution time is proportional to the size of the problem to the power, to some fixed power of the size of the problem. Okay, so let's say if the size of the problem is n, then n to the power 4 is factorial. N to the power of 10, it's still factorial. It is really bad, but it is still considered, factorial. I mean, still considered polynomial. Okay. Then what about the n? What do you think the n stands for? Sorry? Okay, some of you, have heard this term before, but do you remember what n stands for in NP? Non-deterministic. Exactly. Okay, so the n stands for non-deterministic. Deterministic. There we go. Okay, what does that mean? Well, for the lack of a better way to describe it in this class, it basically means anytime you want to spin off a new core, a new physical core in the processor, you can do so. Okay? So in the case of the traveling salesman problem, if you say, I'm going to spin off one thread and have one dedicated physical core to handle that particular route, okay? So you basically will end up spinning up 24 cores in the case of having only 4 destinations. In the case that you have 100 destinations, you can spin up to 9.33 times 10 to the power of 157 physical cores. We are talking about real, actual physical cores that can compute in parallel. Then the problem becomes a polynomial time problem. If you had that special magical computer, then the problem becomes polynomial time. That's what NP stands for. So whenever you have a problem that is known to be NP-complete, which means it cannot be solved with more efficient algorithms, but it can be transformed into one of the known problems in the NP-complete set, then you can tell your boss and say there are no known practical way to deal with this problem. You can fire me and hire other people all you want, okay? But the chances of you hiring a person that can actually solve this problem in a practical way is none, 0. So that's the practical side of understanding computer science, is to keep your job and not get fired. I mean, it really is important, because otherwise, you have this algorithm that worked really well when you're running a small pizza shop, right? As the delivery truck gets a little bit bigger, it gets a little difficult, okay, but it's still manageable. But when you extend it to UPS or anything that has a lot of stops, like 100 stops, it stops working, right? And then your boss will come back to you and say, hey, your program doesn't work anymore. But then you can say, well, it's not my program that is not working. The problem itself is in this particular class of problems, and that's why this approach does not work anymore. Okay? So you will get into these things, when you get to a 4-year university. Trust me, you will get into a class that has a title of either the analysis of algorithms or algorithm analysis, meaning exactly the same thing. But in those classes, you will get into these type of problems where you will assess the time complexity of algorithms and problems. Sometimes it is inherent to the problem itself, regardless of what algorithm you choose to solve those problems. Okay, we are running out of time. I just have one more point to make. With certain problems like sorting, okay, in those classes, they can give you a theoretical lower limit, a theoretical lower limit, and say that there are no algorithms that can be faster than n log n. Do we have n log n sorting algorithms? Yeah, plenty actually. Okay, merge sort is n log n, heap sort is n log n, but can we do better than n log n? Is it worth the time to look for algorithms that can sort in less time than n log n? Well, in those classes, they will tell you, nope, such algorithms do not exist. Theoretically, they just do not exist. So don't bother looking. So those classes are useful. This class is kind of like a foundation to that class that you will probably be taking at a 4-year university. All right, so we are out of time. I'm going to stop the recorder, work on the homework assignment, and if you have any questions, bring it back on Tuesday, next Tuesday. The assignment is due on Thursday.